Hello, everyone. So I want to talk today about how to design a compiler for R. So R is the statistics language, and when you start writing a compiler for it, there is one thing that you notice very quickly, and there is you have a problem with environments and with local variables. And so in R, local variables are in first-class mutable environments. And if that's not clear yet, I'll go into detail a lot. So there's this big gap here between I don't even have local variables and I want to design a compiler. So how do we bridge this gap? So what I'm going to present you today is an intermediate language that we call pir and that we use in our compiler to analyze environments and to figure out what local variables are doing in R. So let's start with how scoping works in R. So we have this very simple example here, and there's a free variable a. That's not what I'm after. So let's assume there is an outer scope. In this outer scope, there is this variable a, and it refers to that variable a. OK, fine. There's this other variable b here. Now, where does this variable refer to? And I think there are two good answers here. One answer is, well, the then block defines its own scope, so it's not in scope. It refers to an outer b. And there is another answer, which is, well, the whole function has one scope, and so the b is in scope, like the assignment that we do here is responsible for the whole function. And in case we don't execute it, maybe it's undefined, something like that. So R doesn't do neither of those two. So what R does is this. It says, well, if you execute the assignment, then it's in scope. If you don't execute the assignment, then it's not in scope. And you will fall through and look in the parent, like in the outer environment for that variable b. OK, it gets worse. So here, OK, so I have a function, f, and I haven't told you yet what this function does. Then I have a local variable a. I call the function, and then I look at this variable a. So what can happen here when I look at the variable a again? Now let's look at the involved environments. I have the outer environment, the gray one, with the function and the a variable. I have the inner environment of the f function. And now I can do different things. I can do this. It looks a bit weird. But what this just means is I look up a in the outer environment and assign it to an a in the inner environment. So that's simple. So this just copies it from the outer environment. I can do this. This actually assigns to the super environment. So now I'm going to change it in the gray environment. So OK, that's still fairly reasonable. Let's say I wanted to protect this local variable a here. I want to extract it so that the f function can't meddle with it. So I'll put it in its own function, and now I clearly should have two separate environments, right? Now they don't have anything to do with each other, right? So I took this part, put it into a function. There should not be any connection. I can do this. I can say parent frame. Parent frame gives me reflectively the environment of my caller. OK, so you might get a feeling that this is bad. I can remove a variable. So what this does, it's as if this a doesn't exist anymore. So now this will return object not found. OK, next step, it gets worse. So I have a function f. It takes an argument q. In this function f, I leak my environment. I again have the same spiel. I have a local variable a q. I look at the argument q, and then I look at variable a again. Now I want to pass something to that function. And one thing I didn't tell you yet, R is a lazy language. So whatever I pass to that function will be evaluated once I look at the argument the first time, once I require the argument. So this will be evaluated here. So I can just remove it in the middle of the function. Right? This, again, will return object a not found, or maybe a exists in an outer scope. And there's a full talk on the craziness of R by Aviral Goel on Thursday. So let me summarize. Local variables are stored in first-class environment. They're accessible to calls, and they're also accessible to promises in some cases. So now, if we want to get a hold of all these things that are going on, so I get back to my initial question, how do I resolve variables and scopes? I noticed that environments, they can change dynamically. And to know where they change, or if they change, I need to figure out where promises are evaluated. To figure out where promises are evaluated, I need to know which functions get called. Okay. But as I showed you, arguments that create promises and also functions, they're just normal variables in the environment. So promises get created by calling functions, functions evaluate promises, so there's circularity here already. But then to trace promises and function calls, there is, of course, even more circularity. So let's look at the IR that we came up to analyze scopes. And this is sort of just an overview of the whole system. So we took the reference implementation from GNU-R, we took the parser, we took the AST, everything is still there. And then we have our own bytecode, we have a bytecode optimizer, and we have a native backend. And from now on, I'm only going to talk about the optimizer, which is using this peer intermediate representation, which allows us to analyze scopes, right? So the nice thing about this architecture is that we can always fall back to the reference implementation. So many times we'll use the reference implementation for some things. So the design of the language, it's an SSA language, and it's explicit about environments and promises. So that's the key thing. And then why did we write our own IR? Well, we tried first with bytecode, with GNU-R bytecode. It was too implicit about things. For example, it assumed that there will always be an environment. And when we want to optimize an environment, that's clearly not what we need. And then we also tried to optimize LLVM, but that was clearly too low level. Like, we couldn't figure out anything anymore once we went to LLVM. So here's our IR. As I said, we need instructions to create environments, okay? So this simple as that. Make environment creates an environment. It takes a list of bindings, and it takes an outer environment. Load variable loads a variable from the environment. Set var just creates or updates an existing binding. That's it, sorry. So only 3 instructions regarding environments. So now how does this work to our advantage? Let's look at the simple example. So this is on purpose very simple because things get hairy real quick. So here I have an if then else, and in one case x is set to 1, in the other case x is set to 2. In the end, I read out this variable. So let's translate this to peer. So first thing we always need to do is we create an empty environment in this case. So this makeEnv creates an empty environment. It's nested in the global scope. So the parent is the global environment called G here. And then there's some branching condition. The condition is stored in register number 2 in this case, and we branch on it. And then we have the then branch where we set x to 1 in this environment. And we have the else branch where we set x to 2 in this environment. And finally, we merge into the final block. And this is now the last line of the snippet on the left. And here we just load the variable again. So it's a really dumb literal translation of what's going on. And the analysis that we have now defined is called scope resolution, and it helps us to get rid of this environment. So at its core, the analysis computes the reaching stores. So it's a flow-sensitive analysis, and if we go through this example, we'll see that in basic block 1, x is set to register 4. In basic block 2, x is set to register 7. And then finally, when we're in basic block 3, x is either register 4 or 7. What does this mean? Now, we want to be able to replace this load here. That's the goal. And we know that it's either 4 or 7. If we come from 1, it's 4. If we come from 2, it's 7. Well, this is nothing else than the definition of a phi in SSA. So this basically means here I can replace it with a phi. And I've successfully removed that load. And I have removed the dependency on the environment. Oh yeah, and also now, since I know where it comes from, I also know that it's not lazy. So I can remove this force instruction that evaluates promises. I'll talk more about laziness a bit later. And I can do further compiler optimizations. For example, I can do dead store elimination. I can remove those stores. I can do escape analysis on the environment. Since it's now not mentioned anymore, it's obviously dead code as well. And so we end up with this very static version of the same code. Okay, so I told you it's hard, and apparently it's super easy. So what's going on? Well, of course, this was a contrived example. Let's say there is a call here. Let's say here we have a call in the middle. And now, okay, this call might reflectively change the environment, so I don't really know anymore what x is going to be when I pass through that call instruction. So this is going to taint my whole analysis. I don't know anything anymore about x. So how do we address that? We have a thing that we call stub environments. And in this case, we're going to say, okay, so obviously environment 1 is necessary, but we're going to use a stub environment. So if we compare those two, and our environment is really a hash map between variable names and values, and you can change the bindings pretty much everywhere. Whereas the stub environment is just really an array, and you can only change values, and they can only be changed locally. And of course, you might say here, well, but how does this work? The call might still mutate the environment. Oh yeah, that's what I said. So now with those assumptions, we can now say, okay, the call doesn't change the environment. But of course, those are only assumptions. So with stub environments, we actually have some form of de-optimization here. We need to say, so if this call happens to reflectively access the stub environment, we have all the information to produce a real environment, but the rest of the code is going to be invalid after that. So we need to de-optimize. So I guess the design principle here is sort of so we try to analyze as much as we can statically, and exactly at the points where that doesn't work anymore, we will put assumptions that allow us to keep the analysis precision that we need to transform it. So now a bit more intricate is inlining and getting rid of promises in this framework. So I need to extend the language a bit. I need another instruction to create closures. And I need something to create promises. So this make arg instruction creates a promise. A promise is like this lazy argument, which is the expression of the argument and the environment where it was created. It will become more clear later. And then I need the equivalent, or like the dual of it, the force instruction that takes a promise and evaluates it down to an argument. So let's look at this when we look at this example. So we have the f function, which is the identity function, more or less. And we're going to pass a local variable x to it. I mean, so if we translate this snippet here, we create a closure for f, which means we take the expression of f, we bundle it with the environment. Then we create a promise that we're going to pass to that function, which again means we take the expression of the argument and bundle it with the environment, and then we're going to call that function. The function itself is going to load the argument. It's going to create an environment where b is named, where the first argument is named b. Then it's going to evaluate that argument, and it's going to return it. And then the only piece missing is the promise expression. The promise expression is basically this thing here, what we're going to pass to the function. And it's loading the argument x. It's forcing it, because x might also be a promise, and then returns it. So what's going on here is we create the promise, we pass it to the function receives it as its first argument, the argument gets forced, and we end up evaluating the promise. And this is sort of the analysis that we would have to do to figure out what's going on in this program. But what we want to do instead is then analyzing it all at once is we want to inline it step by step. So we can do it in this IR. Let's make some room here. First thing I want to do is I want to inline this call to f. So easy as that, I just move the body up here. And again, this is only easy because we designed for it to be easy. So the f function has an environment. The environment might be visible. I need to inline the environment with the function. You might think of another function that does this, that executes this ls function, which gives you the name of all the variables in scope. If you would inline at the source level, well, you would see more than just b in scope here. So I need to retain the environment when I inline. Then the next thing is I'm going to search for the dominating force instruction, because the other fact about promises is they only get evaluated once. So it's this call by need strategy. The first time you require an argument, it gets evaluated, and then it gets memoized for further uses. So I need to find where it's evaluated the first time. And for that, I search for the dominating force instruction. OK, here it's easy. I found it. And then what I can do is I can inline the promise expression at the place of the dominating force instruction. I'll move it here. And now I've picked up this dependency here. Basically, when I evaluate x, this could be a promise, and this promise could observe the environment of this f function. So if we look at the force instruction, it has this weird notation where the environment is outside of the parentheses. And by that, we just mean that there's a dependency on the environment. It could be reflectively accessed. And let's just assume x doesn't do that. In this case, this dependency vanishes, and I can remove the environment, and I can remove the creation of the promise, and I've successfully removed the simple identity function, and I've successfully removed the promise b. And I end up with just evaluating the argument x. OK, so when can I assume that x doesn't do anything funky? Well, what I can do interprocedural analysis. Basically, I can try to figure out what x does. I can use stub environments again, like I described in the case of the call. It's the same thing here. I could say, like, let's just assume the promise doesn't do anything to the environment. Or I could use this mechanism that we call version dispatch. So when I call a function and I pass it a promise, and I don't know what this promise is going to do, then I'm going to call the most generic version of that function. But often, it's very easy to see that a promise is not going to do reflection. So in this case, I can call into another version of this function f that assumes that the promise passed don't do reflection. And so I can produce more optimized code in those cases. So this trades code size for basically analysis precision in that case. So to summarize, we try to, when possible, lower our variables to peer registers. We try to inline promises and then get rid of environments. So how well does it work? And so personally, for me, this was the main contribution. So it was not clear to me at all whether it's possible at all. So, and we found out that, yes, in some cases, it is possible. If you have the right tool, if you have the right IR, if you model the problem correctly, then you can sometimes lower R variables to registers. And to be a bit more precise, so we found that in some 12 to 65% of closures, we were able to remove environments. And then this leads to 30 to 90% of less environments created at runtime. And this was just for the benchmarks that we used to evaluate it in the paper. And then we were also able to show with some experiments in the paper that basically scope resolution and promise inlining enables further compiler optimization. So if you disable those two passes in our compiler, then it kills most optimizations that come later. So in conclusion, so we have this implementation. It's called Arsh, and and you can try it out. It might be slowly getting to the point where I would not tell you not to use it. So maybe try it out and give us feedback. And in conclusion, well, the language is really bizarre and needs very specific kind of analysis to be able to compile it. But nevertheless, it is possible to reason statically about some R programs. And the key insight is really you need to explicitly model what's hard to understand in the language you want to optimize for. And I want to finish with just telling you that if you have an extremely slow running R script that spends lots of time in R, just please hand it to us. Thank you.
So we have plenty of time for questions. A question about the sort of the first part of the talk, which was the optimization of the environments. So you mentioned that you basically do as much as you can statically, and if you can, you will eliminate the environment, and you eliminate the forcing of promises and such. But if that's not possible, then you will inject a different, simpler version of the environment, the stub environment.
Mm-hmm.
Did I get it?
Yes, yes.
Right. So I was wondering if there's any notion on how many times you can actually move everything.
How
many times you have to leave that stub environment.
Yeah.
And
So
also, what's the performance implication or difference between actually using the stub environment versus leaving the original ones, the hash maps?
Yeah. So using the stub environment is a lot closer to not using an environment at all than to using the full environment. The full R environment is really relatively slow, and the main reason for that is also that we're inside, that we're using the existing reference implementation, so we can't really optimize the slowest version of our environments. So the stub environments are really very close to not having environments at all. And what was the second question? Oh yeah, the numbers. So the numbers are in the paper, and some I can't tell you on the top of my head. I think it was something like in a third of the cases it was completely removed, and 2/3 were stub environments. But don't quote me on that.
The performance difference between executing with stub environments and executing with regular environments?
So it really depends on what kind of. So this is just like the pre-processing to be able to more optimizations, and so we explicitly. So we explicitly.
They are manifested physically, right? In
Yeah.
the code.
Yes.
The stub environments.
Yes. Yeah. So you create them. You might need to update them, and they live on the heap, and so there is an overhead. Yes. Yeah.
Do you do procedure inlining, and is the lookup names for the procedures that you're actually called going through all the same environment mechanism? So if you're just calling some function f, right, that's a lookup in
Yes. Yes.
Do you actually inline functions?
Oh yeah. So to be able to inline functions, you need assumptions. So if they're local functions, then just being able to trace local variables allows you to inline statically. For global functions or functions from packages, you need speculative inlining, and there we have like an assumption that just guards that the function wasn't overwritten. If it wasn't overwritten, then the inlining is correct.
Are the structure of those global environments, are those similar or are the same?
They're the same. They're the same. Yeah. Actually, loading a package is implemented by adding the package namespace above the global environment in the scope chain.
Even with local inlining, functions inlining, don't you have to have some kind of
Absolutely, yes.
Another question? I have a question about promises.
Mhm.
In the code, you showed you had two force operations where I would have assumed there would be just one,
Mhm.
because your thunk of the promise was actually doing a force at the end,
Mhm.
but there was also a force of the promise in your main code.
Right, so the function, yeah, I know what you mean.
So I'm just wondering why.
Question, please. The speaker maybe, because I couldn't hear the question.
I'm going to repeat it. So the question was, why do we have this force instruction here, right?
Yeah.
The reason is that many things in R are actually eager, even though the language itself, like when you call a function, then it's lazy, but many other things are eager. So even just mentioning the x here is an eager operation on x. So mentioning x will force whatever promise might be stored in x.
Okay. But you know that you're getting there because you're forcing %6.
Yeah, at some point I will figure it out and we will remove the redundant force, yes. But this was just like the literal, or the very simple translation, and it might not be clear yet that this is a redundant operation. Right? So the force, in case it encounters a value, it just does nothing. Yeah.
More questions? All right. Thanks, Olivier.
Okay.